So today we're going to continue linear sketching. And specifically, we're going to look at an example of graph sketching, which is a technique that was introduced by An, Guha, and McGregor in 2012. And today you're going to see an algorithm they developed using linear sketching for finding the spanning forest of a graph being updated dynamically in a data stream. But since then, linear sketching for graphs has been used to solve numerous graph problems, matching, minimum spanning tree, and a ton of others as well. I think it's a really cool idea and to me unexpected. So let's say dynamic spanning forest. So, edges are inserted or deleted from an n vertex graph, and then query output a spanning forest. Right. Which you can use, of course, to say find a path from like determine connectivity, ST connectivity. Is there a path from S to T, or to find a path from S to T in an undirected graph? This is all undirected, I should say. And this can be modeled as a problem in the strict turnstile model. Right? Because you imagine that you have a vector x, which is in 0, 1 to the n choose 2. Well, let's even say, natural numbers to the n choose 2, where x, uv is the multiplicity of edge uv in the graph. Okay, so if it's a simple graph, then it's always going to be 1 or 0. But if it's a multi-graph, you might have many copies of an edge. Okay. So I think I might have mentioned this before last lecture when I introduced linear sketching in the turnstile model. I gave this as an example. Graph streaming is an example where the strict turnstile model makes sense. So if someone says, add edge E, that's the same thing as saying update, UV plus 1. And similarly, delete E is the same thing as update. In the turnstile model, update UV minus 1. Okay. So by the end of today's lecture, you'll see how to do this in low memory in a data stream. Okay. I should say that if there are no deletions, this problem is trivial, right? Because you just remember, basically you just do union find, right? So, that gives you speed, but if you don't even care about speed, if all you care about is memory, then whenever you see a new edge being inserted, then, if it connects two vertices that are in different connected components, then you store the edge. If it connects two vertices that are in different connected components, or the same connected component, then you can safely ignore the edge, because since there are no deletions, you know that since these vertices are already in the same component, they will always be in the same component from now on. So this edge is safe to ignore. Now, a spanning tree has n-1 edges. A spanning forest has n-k edges, where k is the number of connected components. But in any case, it's at most n. So for each edge, you can just remember, you can just store all the edges, right, in the spanning forest itself. And you're going to store at most n-k edges, which is at most n. Each one is log of n squared bits. You have to remember both endpoints. Log of n squared is the same thing as 2 log n. So this algorithm uses memory at most 2n log n bits, O of n log n. Right, so I just want to say that this is trivial in insertion-only streams. to achieve O of n log n bits. Okay. And maybe I'll leave it to you as an exercise. Now that you've seen lower bounds via compression arguments, you can prove also that there is no algorithm that uses fewer than n log n bits. Okay. I mean, one way to do it is to, via compression argument, is just to say, if there were such an algorithm, then I could use it to define an injection from the set of all trees on n vertices into, let's say use s bits of memory into binary strings of length s. Therefore, s has to be at least the logarithm of the number of trees on n vertices, and that already gives you an n log n lower bound. Okay, so this is the trivial algorithm, but in strict turnstile, you can't just remember the edges in a spanning tree in the spanning forest. Why not? Because here's a very simple example. Let's say that I insert this edge first. I insert this edge second. Then I insert this edge third. You're going to say, oh, I don't need to remember edge number 3 because those two vertices are already in a connected component. Right? Then I delete edge 1. And then I delete edge 2. And now the graph looks like this. But since I didn't bother to remember edge 3, I won't realize that these two vertices at the bottom are in the same connected component. I'll think that I have the empty graph. So it's not clear, what should I be storing so that when people delete edges that, when people start deleting edges that I thought were being used to connect up different components together, I somehow can find replacement edges that still still cross that bridge. And the surprising fact, though, is that it is possible. So just so we're clear, the absolute trivial algorithm is O of n squared bits of memory. Right? For each possible edge that could exist, remember if it's there or not. Or another trivial thing is m log n bits of memory, where m is the current number of edges. So just remember every edge that you've seen. If someone deletes it, you can delete it from your memory. If someone inserts a new one, you insert that into your memory. If you have m edges, that's m log n bits, or O of m log n bits. And because the issue there is, you could have an algorithm, you could have a graph that maybe at the end is sparse, but in the intermediate time step is very dense, right? I could insert n squared edges and delete all but 5n of them. And I don't want my memory to blow up to n squared. What we're going to see today is the AGM sketch is that, in fact, there's a randomized algorithm that uses O of n log cubed n bits and succeeds with probability at least 1 minus 1 over poly n, where the exponents in the poly can be whatever you want. More specifically, it uses O of n log squared n log of n over delta bits and succeeds with probably at least 1 minus delta. And interestingly, we know that this n log cubed n bound is actually optimal. We know that this thing, that bound is optimal for dynamic spanning forest. That's something that I proved with watching you last year. And dynamic spanning forest is, you have to output potentially up to n minus 1 edges, right? You have to remember. You have to, one. You might say, well, if one of the reasons that might be hard is because my output is so large. My output has size n log n bits. So it's, of course I need at least linear memory. Getting the log cubed n is, not as obvious, but of course I need at least linear memory. But Huacheng actually even strengthened this. He showed this is optimal for just simple connectivity. This is something that's online now, but he submitted to a conference that would appear next year. So here, right, the answer is a single bit. Is the graph connected or not? I just want to know 1 bit. He showed that even for that 1 bit, even for that problem with a 1 bit answer, you can't do any better than actually being able to find a spanning forest. You can't do better than n log cubed n bits. So that was a bit surprising. Another thing I'll say about the AGM sketch is it doesn't only work in the streaming model. It also works in other models as well. So let's consider the following model. I have a graph. Right. Okay. And each vertex, it's a distributed model. Each vertex V knows who its neighbors are. But it doesn't know anything else about the graph. So this is, up to something like n-1 bits of information about the graph. And then there's some central server here who doesn't know anything. There's some public randomness in the sky. The vertices know that random string. The server knows that random string. And then just knowing their own neighborhood and knowing that public random string, each vertex is supposed to send a message to the server. So message 1, message 2, message 3, message 4, message n. And the server then has to output a spanning forest. And what AGM shows is can accomplish this with the max message length being O of log cubed n bits. And it's randomized and it succeeds with probability at least 1 minus 1 poly n. Okay. So there's some kind of distributed, I guess there's another vertex that I forgot to draw. Doesn't matter. There's some scheme for a distributed computation which minimizes bandwidth, right? The naive thing would be that every vertex sends its entire neighborhood to the server, then all the messages would be linear in length, omega n bits. And the AGM sketch is saying, actually, each server only needs to send a message of length log cubed n. So before we talk about how the AGM sketch works, I need to introduce a couple of primitives, some subroutines. And these are useful subroutines to know about because they come up in other places as well. Okay. Later in the semester, when we talk about, for example, compressed sensing, you'll see that one of these is very related to that. Okay, so one subroutine. So first, let's talk about some subroutines we need. One is something that I'll call k-sparse recovery. And the other thing is something I'll call support find. So these are both, let's say, I'll describe them both in the terms Oh, okay, I was muted. So it seems I lost connectivity for a few seconds. Can people hear me?
Yeah.
Okay, great. So let's continue. Um, I'll describe both of these problems in the turnstile model. We need it for strict turnstile, but the solution is basically the same for both. So what are these problems? So k-sparse recovery. I mean, we know what the update model is, right? In turnstile, the update model is given. Like update I delta means add delta xi. So the only question is what's the query? So query, if the support size of x, the number of non-zero entries in x, is at most k, we must return x exactly. Else can output anything. And support find when someone queries that data structure, return any I such that xi is not equal to 0. Okay. Remember, x is this vector being updated in the turnstile model. So, I mean, so support find maybe is the easier one to talk. Give you an example of like how to think about it. So we have this graph. We're inserting edges. We're deleting edges. Someone says query and support find. What they're really asking is, tell me any edge that's still in the graph. Okay, it's not clear how to answer that, right? Using low memory. I mean, if you try to sample and remember a random edge, then you say, well, if it's a random edge, then with high probability, even if Jelani deletes some edges later, he probably won't delete my edge, right? But that's a wrong way of thinking, because what if I insert a million edges and then I proceed to delete 999,999 of them? There's only one left. It's very unlikely that the sample that you kept is the one that survived, right? But a support find data structure has to handle that scenario, and it should succeed with probability at least 1 minus delta. Okay. I like to usually, when I introduce support find in talks, I like to talk about it in terms of what I call the fruit game, which is that you're holding a basket of fruit. I come in and I start just dropping fruits in your basket. And I can also reach in the basket and take out a fruit. So, you see me put an apple in your basket. You see me put another apple. You see me put an orange. And then later you see me take out an orange, etc. And then I ask you, tell me any type of fruit that's still in your basket. Okay. And I don't allow you to look in the basket to remind yourself. You can just look at what I've been putting in, and you can look at things as they come out, but you can never remind yourself by looking in the basket. And it's not trivial to solve this problem, but it turns out there is a solution that uses only logarithmic or polylogarithmic space in the universe size. So in a graph on n edges, the universe is of size n choose 2. The number of possible edges in a graph is n choose 2, which is about n squared. So you're going to use polylog n bits of memory, and you're going to be able to solve support find. And of course, this is a necessary requirement. To be able to solve support find is necessary to solve spanning forest, because spanning forest, you're not just returning one edge in the graph, you're returning a bunch of edges that form a spanning forest. So spanning forest is definitely much harder than, or it's definitely at least as hard as support find. It turns out to be much harder, but it uses support find as a subroutine. Okay, good. So I want to tell you, how to actually implement data structures that solve these two problems. And then finally, we'll see how to use these data structures to implement to come up with a new data structure, the AGM sketch that solves dynamic spanning forest. This is actually going to be a deterministic data structure. And I'm going to make the assumption that I have bounded entries in my histogram. just to make it simple, let's say poly n. So, of course, in a dynamic simple graph, the entries of x are always either 0 or 1. So indeed, the magnitudes are bounded. But in general, let's say I'll just assume that the entries are bounded by some polynomial in n. It doesn't have to be polynomial in n. If you have some upper bound, then you'll have a space complexity that depends logarithmically on that upper bound. Okay. So it's going to be a linear sketching approach. Okay. And what I'm going to do is I'm going to pick, let's say that this upper bound is, let's call it capital T. I'll pick a prime that's bigger than, let's say, 2nt. And I'll do all arithmetic over the finite field on P elements. Right, so the point is, I'm going to be, or actually, I think that's fine. So I'm going to be doing arithmetic over, I'm going to be adding, some of these numbers together. I'm going to have counters, and look, each number is at most t. There are n numbers, at most n numbers that I'm going to add together in any counter. So I'm going to have numbers that are, the true numbers over the integers are never going to be bigger than nt. So as long as I pick a prime that's bigger than nt, even if I do things mod p, I haven't changed anything. Okay, but I want to work with some bounded precision here so that I guarantee, so that I can actually do some bit counting. Okay, I don't want to work with real numbers because I'm going to divide stuff, etc. So I prefer to do the division over fp. So remember, what I'm storing in memory is a linear sketch. So if I remember, what k-sparse recovery says that if x is k-sparse, my query has to be able to return x exactly. So in order for that to be true, at the very least, I need this map, x gets mapped to pi x. I need that to be an injection when you consider it on the set of all k-sparse vectors. So I need that for all x not equal to y, where x and y are both k-sparse. K-sparse means at most k non-zero entries, remember. Pi x is not equal to pi y, which is the same thing as saying pi x minus y is not equal to 0. Okay. So in other words, I want to say that, so and notice, by the way, that this vector here is at most 2 k-sparse. Right? X minus y as a vector has at most 2k non-zero entries, since x and y each have at most k. So it suffices to have that no 2k sparse vector is in the kernel of pi. Okay. So let's look at, what does that mean? So let's say we have a 2k. So I want that for all 2k sparse vector z, pi z is not 0. So here's pi. Here's z. Z is sparse. Say this is z is sparse, so it has some non-zeros. Everything else is 0. Sorry, so these parts, the starred ones are the ones that are not 0. Or maybe I should use a different color. These red stars are non-zeros. So remember now, this is just a general fact about linear algebra. Pi z is the sum over I of zi times pi I, where pi I is the ith column of pi. Right? This is just a fact about matrix vector multiplication. So kind of the only things that are relevant in pi z are the columns that correspond to non-zero entries of z. So, here's one, here's another one, here two right here. Here's another one. These are the only columns that are relevant in the multiplication pi z. So I can look at just those 5, let's say, or 2k, at most 2k columns. I'll call this pi, let's call it S, where S here is the support of Z. Right, so it's pi where you only keep the columns in the support of Z. That's pi S. Pi S is you only keep the columns in S. So that what I want is that for all S of size at most 2k, pi S has full column rank. In other words, the rank of pi S should be 2k. So let me show you that there is a matrix that satisfies this. It's something called basically Vandermonde, or the transpose of a Vandermonde matrix. So pi will be this matrix. One x1 squared, x1 to the m minus 1, 1 x2 to the m minus 1, or again, m is the number of rows, 1 x3, etc. Okay. So notice that if you take any, if you take any submatrix of this with 2k columns, right, it just kind of looks like, it's kind of the same pattern. It's a Vandermonde matrix, okay? And if you choose, so let's say you take here 2k columns, what I'll do is I'll also take 2k rows. So I'll set m, I should say that all the xi's are distinct. So notice that this already means that I need p to be bigger than n, right? For this to be possible, or at least n anyway. I'll choose m to be 2k, so any m by 2k submatrix is a square of Vandermonde matrix. And luckily for us, there is a theorem. I might have a sign error, but I think it's this, which says that if you take a square Vandermonde matrix, its determinant of a square Vandermonde matrix is, let's say, pi S, basically the product over j less than j prime in S of xj minus xj prime. And the point is, since none of these, since these are all distinct, xj minus xj prime is always non-zero. You're multiplying together a bunch of numbers that are not zero, so the product is non-zero. So this is not zero, right? So that implies by linear algebra that it's full rank. So it doesn't have any non-zero vectors in its kernel. Okay. So that's it. So we've constructed a matrix that has the desired property. And now, at least in principle, we can use it to solve k-sparse recovery in exponential time. So let's say someone says query. So remember, we're given basically y equals pi x, or this is k-sparse. And we want to find x. So how do we do it? we just do a for loop. We just say, look, for all, just loop over all S, which is a subset of the columns where S has size exactly 2K, and let denote X prime as pi S inverse applied to Y. And then just say, if the support size of X prime, we know that the support size is going to be at most, we know that the support size of X prime is going to be at most 2K, right? Because pi S has 2K columns. But we're looking for something that's K-sparse. So it might be too dense. It might not be K-sparse. It's only 2K sparse. So if the support of X prime has size bigger than K, or let's say at most K, I should say, then return X prime with, with zeros added in the right places. So what do I, that's a little informal. What do I mean by that? The point is, I guessed that the support of X was, we know the support has size, let's say 2, but I guessed the set of size 2 times 2 of size 2K. Right? So I guess that the support was contained in these 4 elements. And then I solved the linear system. And when I solved it, it gave me a vector back that was actually at most 2 sparse. So it said, actually, this is a 5, and this is a 7, and then these are zeros. And then what I'm going to do is I'm going to just pad the rest with zeros. And then I'm going to return that as my answer. So that's what I did. That's how I answered this thing. And the point is, this is guaranteed to work because there should only be one, right? We said that this thing is an injection on the set of K-sparse vectors. So there aren't going to be 2 different S's that give you back valid, that give you back K-sparse vectors if you solve the linear system, because otherwise the thing wouldn't be an injection. Those 2 different K-sparse vectors for S and S prime would both map to the same Y, which means it's not an injection. That's impossible. So good. So that's it. The total memory here is K log P bits, which, if I assume that P is at most poly n, is K log n bits. In fact, K here, the constant in the big O is 2, right? The number of rows I have in pi is 2K. So it's a 2K log n bit algorithm, a 2K log P bit algorithm. Now, the thing that isn't so great about this algorithm is that the running time to answer query is exponentially big. How many sets of size 2K are there? N choose 2K, which is roughly n to the 2K. So this is an n to the O of K time algorithm, which, we're going to instantiate this later with K being something that's not constant. So it's going to be like a quasi-polynomial time query algorithm, which isn't great. It's possible to have a poly K log n query time algorithm. It's known as syndrome decoding, which is related to something called Prony's method. We might talk about it later in the course when we talk about compressed sensing, but I'm not going to talk about it today. So syndrome decoding, it's related to decoding for error correcting codes, in particular, like Reed-Solomon codes. So, it's a little, I think I would have to, pivot what we're talking about considerably to cover it today. So I don't want to do that. Okay, but we'll just talk about memory. So we know that now that there's a low memory algorithm for this problem. So now we're going to use it to solve support find. Remember, support find says when someone says query, return any I such that xi is not 0. So how are we going to do this? We're going to use a trick that you've learned before when we talked about, remember we gave a few different algorithms for distinct elements toward the beginning of the semester. We talked about Flageolet-Martin, we talked about the KMV, K-minimum value algorithm, and then we had a lecture on the geometric sampling approach. So here you're going to see the geometric sampling approach strike again. So we're going to have a k-sparse recovery structure here. And then we're going to have another log n k-sparse recovery structures. And then we're going to have a hash function h, which maps the universe into 0 log n. Actually, let me call this KSR 1 and 2. Well, let's just say for now that it's totally random. This can be relaxed to some, bounded independence. I'll talk about that later. But we want that the probability that h of I is equal to j to be, roughly 1 over 2 to the j. Okay. It will be 1 over 2 to the j, except then the sums of the probabilities won't be 1. So the very last level, the probability won't be 1 over 2 to the log n, but it'll be whatever it needs to be to make the sum be 1. Probably it'll be that up to a factor of 2. Okay. And when someone says update I delta, what I'll do is I will always, let's call this KSR 0. I will always feed every update into KSR 0. But then I'll also feed it into a random one of the other KSRs based on h. In particular, I'll send it into KSR. I'm sending it into KSR sub h of I. Right. And because h is biased to usually be small, right? The probability that h of I is big is exponentially small. So usually h of I is 1. Once in a while, h of I is 2. Even less frequently, it's 3, etc. So the majority of these updates will get sent to KSR 1, but some will get sent lower as well. Okay. So that's it. That's my data structure. So and I'm going to do this with delta, let's say, if I want failure probability delta, oh, these are, good. Actually, I think, yeah, I'll instantiate each KSR data structure with k being some constant times log 1 over delta. Okay. So delta will play a role in how I set k. Remember, these data structures KSR are deterministic. They always work. But you have to tell it what k to use. And if you want a bigger k, you spend more memory. So the total memory here, each one of these KSRs uses k log n bits, which is log 1 over delta log n. And you have log n of them. So the total memory is something like log 1 over delta times log squared n. Okay. And it's known that even for a support find, this is optimal. And this is a lot of authors. Kapilov et al. 2017. To be more precise, I mean, the thing is that, you can solve this. If they're binary vectors, then of course you can always solve the problem in n bits. You just remember like which items are in the set and which aren't. So log 1 over delta log squared n is not always optimal because you could, what if delta is 1 over 2 to the 2 to the n? Then log 1 over delta is 2 to the n. This algorithm would use 2 to the n memory. But basically at some point, once delta becomes exponentially small, you might as well just solve the problem by maintaining the entire histogram in memory explicitly. And that's basically what this paper says. It says up to a certain point, this algorithm, this geometric sampling algorithm is optimal. And beyond that point, you might as well just use a histogram. Okay. So good. So now let's reason about how you would answer a query. Okay. So maybe I'll ask you, any of you have a suggestion on what should you do to answer a query? Remember, what I'm trying to do is I'm trying to find some I such that xi is not 0. Any takers? Maybe let me start with a hint.
Check the first block that's non-zero.
When you say the first, what do you mean by what is the first, what is the last? Where are you starting counting from? Where do you start counting from?
Starting from the bottom.
Yeah, starting from the bottom, right? So the point, so how many
KSR log n.
Right, KSR log n. How many support elements do you expect to land in KSR log n? A 1 over nth fraction of them, right? And if the support size of x is not that big, let's say it's root n, probably nothing is landing there. Probably KSR log n is empty. Okay. So, and by the way, this is of course very similar. A lot of these geometric sampling ideas look similar, very similar to what we saw in distinct elements. So you look in KSR log n, oh, it's empty, right? You query it, it gives you back the empty vector, the 0 vector. You're like, oh, nothing's there. Then you look at KSR log n minus 1. Oh, nothing's there either. And you just work your way up until the very first level from the bottom that returns at something that's not 0. Okay. And then once you have that, you just return anything in the support at that level. Okay. Now, why did I set k to be log 1 over delta, and why should this work? Well, the point is, when does this fail? This fails if, remember now, KSR is a deterministic algorithm. If the vector actually is k-sparse, then it's very unlikely, sorry, not unlikely. If the vector actually is k-sparse, with 100% probability, you'll get the vector back. It's a deterministic algorithm. So the only way this can fail is if, you try to give it, remember the behavior is undefined. The KSR algorithm, the behavior is undefined if it's not k-sparse, if it's actually a denser vector. So the only way this could fail is if, as you're working your way from the bottom, at some point, you have this, you run into a vector that's not actually k-sparse, and then the data structure at that level does the wrong thing. Like, it just acts arbitrarily and gives you back an element that isn't real, and then you output that, and you're wrong. Okay. But for this, you basically can use the Chernoff bound, right? You can say, look, let's say, at level KSR log n, I only expect 1 over root n elements. I mean, that's less than 1. I don't expect any elements. I only expect 1 over root n elements. What's the probability that even though I expect 1 over root n elements, I get more than k elements, more than c log 1 over delta? That's very unlikely by the Chernoff bound. Okay. And I could basically do that working my way up from the bottom up until, let's go up until, let's say there's some magic level here. There's some kind of prefix or suffix of levels where the probability that any of these levels has more than k items, is at most delta over 2. Basically, it follows by the Chernoff bound and union bound. So the failure probability at the levels is geometrically changing, right? Because let's say one of those levels, and this by the way is the level where, let's say, actually, how do I want to see this? So this is the level, say, level where you expect some other, C prime log 1 over delta elements. And imagine that C is some constant that's much bigger than C prime. Okay. So if you look at this region of levels, you can argue just by a Chernoff and union bound that none of them gets more than C log 1 over delta elements via the hash function. Meanwhile, you don't just want to say that you never get tricked by something that has too many elements. You also want to say that there is going to be a level that does have at least one element, right? Because I do have to return an element at the end of the day. So let's look at this level right here. I want to argue that the probability that this level receives 0 support elements is also small, it's less than delta over 2, which also follows from the Chernoff bound, right? Because how many do you expect to be there? You expect C prime log 1 over delta to be there. Think of C prime as a big constant. What's the probability that you don't have C prime log 1 over delta? You have 0 elements. You deviated from your expectation by a lot, right? And the probability that you deviate by that much is exponentially small in this log 1 over delta. So if you pick C prime to be big enough, the Chernoff bound will tell you that this is at most delta over 2. So if none of this region of levels has too many elements, that means all of them are succeeding. They're all giving you valid recoveries. And you know that the top one does have at least one element in its support, then that guarantees that somewhere in that region you're going to find an element and you're going to return a valid element. Does that make sense? Basically, the reason I'm choosing K the way I chose it is to basically apply the Chernoff bound to get my failure probability to be exponentially small in K, which is going to be something like delta failure probability. Okay, good. Now, notice that I also had this KSR 0, which received every update. If people remember the older geometric sampling algorithm I described for distinct elements, why do I need KSR 0? I haven't talked about it yet. Why is it there? Right, you can think, basically, I have two components here, right? I have this geometric sampling thing going on. But then I also have this data structure KSR 0, which is receiving every single update. I've only talked about needing this geometric sampling part, right? I say basically, there is this level, this red box level in the middle somewhere, where I expect log whatever C prime log whatever delta elements to survive. So I'm guaranteed that I expect that, and I'll actually have one survive with high probability. So somewhere in that suffix, I'll get a return value that works, right? So everything works just in this big yellow blob. Why do I need the top yellow blob? Why do I need the KSR 0? Maybe I'll give you 5 more seconds. Okay. So the reason is, right? What is this level?
Wait,
what is this is yeah, go ahead. Yeah.
Is it if there are too few elements?
Yeah, what if too few elements in the support of X itself? What if X itself is already super duper sparse? Its sparsity is less than C prime log 1 over delta. Then this red box level doesn't exist, right? Because what is that red box level? It's the level where the support of X over 2 to the j, where level j, is roughly c prime log 1 over delta. But if the support of x has size less than c prime log 1 over delta already, then there is no such j, right? But that's an easy case. If x itself is already sparse, then I don't need the sampling. The sampling was to ensure that x is sparse so that k-sparse recovery works. But if x is already sparse, I don't need sampling. I can just directly use k-sparse recovery. So the overall query algorithm is, I first look in the geometric KSRs, starting from the bottom. I look at KSR log n. I look at the one above it. I look at the one above it, all the way up to KSR1. The very first time one of those returns me a non-zero vector, I return any element from its support. If all of them to give me a 0 vector, then I just return something from the support of KSR 0. And if KSR 0 says it's a 0 vector too, then I'll just throw my hands up and say, you know what, probably x is just the 0 vector. That's probably why this is happening. Okay. Does that make sense? And you know, if the problem is also,
how do you go from a non-zero KSR to an element in the support?
oh, so
Like,
yeah,
how do you
so
know the element which the hash function maps?
how do you
to that
know?
block?
Sorry, say one more time. So
Like if you have the
yeah.
non-zero KSR block,
yeah.
how do you get the support element?
Right, so if you k-sparse recovery, remember how k-sparse recovery works? So I mean, I guess I didn't say, but it returns to you, when you query a KSR data structure, it returns to you my k-sparse vector x is as follows. K2 is 7, K7 is 4, and K11 is 22. It tells you the support and the values, right? So if one of the KSRs tells me that, I'll just look at the first value, if the first index it gave me with a non-zero value, and I'll just return it, right? If you look at the KSR data structure that we described on the previous whiteboard, there's this exponential time query algorithm which guessed S, solved a linear system, and if that linear system gave you a k-sparse vector back, it returned it, right? So the point is, you just look at, it's basically will tell you S, and it will tell you all the values on S. At most, half those values are 0 because S has size 2k. Or sorry, not at most half, but basically, one of those values will be non-zero if it's a non-zero vector, and then at least half of them will be 0, but that's fine. Just return anyone that's non-zero. Does that make sense?
Yeah.
Any other questions? Okay.
Doesn't every
Yeah.
I end up in some KSR that's not 0?
You said, doesn't every support element end up in some KSR?
Yeah, for any I and
Yes, it does.
so why would all KSRs report 0?
But I don't just actually, that's a good question. I think you're right. Maybe I probably don't even need the KSR 0 for exactly the reason that you said. So good. You simplified this picture even a little bit more. Yeah, I don't think you're right. I think even if the vector originally is sparse, then I know that the union of the supports of all the KSRs combined is at most C log 1 over delta. Oops, I lost. So anything that receives a non-zero, any KSR that receives something from the support will have support size at most K as well. So yeah, I think you're right. I don't even need KSR 0. Okay. Does that sound right to you?
Yeah, I think so.
Okay, good. Any other questions? Okay. Yeah, I guess we did need such a thing with distinct elements, but you're right. For this particular problem, it seems like we don't need it. So now, in the last half an hour, let's talk about dynamic spanning forest. And this is the AGM sketch. Okay. What we're going to do is so okay, one is, at the end of the day, notice that both support find and case-sparse recovery, like the algorithms I've described, are linear sketches, right? Because at the end of the day, you know, what are we storing in case-sparse recovery? We're storing a matrix vector product. So that's a linear sketch. You're maintaining some pi times some vector. And then what are we doing in the support find data structure? We're hashing, and then we're, yeah, I mean, at the end of the day, like whenever there's an update in support find, some set of counters get added to in a linear fashion, right? We add delta times some coefficients in some buckets. So everything we're doing here is linear. Okay. Or, you know, if you want to look, you know, more, if you want me to actually draw the matrix. So the matrix for, let's say, support find looks as follows. So if you look at the first column, H of 1 is some level. So basically you can think of the rows as like being divided into like log n blocks. So this is like region 0, region 1 up to region, oh, there's no region 0, it's region 1 up to log n. And remember that there's a hash function h, which tells you for each column or for each entry, like where does it go? Which block does it go to? So let's say that h of 1 is 2, then everything outside of block 2 will be 0. And then in block 2, you'll have like column 1 of a case-sparse recovery sketching matrix, etc. Okay. I mean, I don't think it's super informative to draw out what the matrix is, but this is what the matrix is. So it's a linear sketch. Okay. So for dynamic spanning forest, what I'll do as follows. I'll pick R, which is going to be theta log n, support find sketching matrices. Let's call them pi 1 up to pi r. Oh, and I did want to say one thing about this picture. Notice that I said h is totally random. Why did I say that h is totally random? Because ultimately I was applying the Chernoff bound to say that at a level that's too deep, it's very unlikely that you have too many support elements land there. And also at the red box level, you will have you will have a non-zero number of elements, support elements with high probability as well. And the Chernoff bound, you know, when I wrote the Chernoff bound, like in the lecture notes, I assume that the random variables that are being added together are independent, right? What are the random variables that are being added here? If you focus on a particular level J, then kind of xi is an indicator, or let me not say x, yi is an indicator random variable for the event that item I was hashed to level J. And then I'm summing up over all the yi's, and that tells me how many elements got hashed to level J. So that's my sum of independent random variables that I'm applying the Chernoff bound to. Okay. One thing about the Chernoff, and I won't justify it here today, but one thing about the Chernoff bound is you can show that basically if the Chernoff bound is giving you a failure probability of delta, then it's enough if the summands had only been roughly log 1 over delta y's independent. They don't actually need to be fully independent. So since we're shooting for failure probabilities from Chernoff on the order of delta in this argument, it's enough that h is drawn from a log n y's independent family. So you can actually store h. In less than and linear memory. Log 1 relative y, sorry. So it really is an honest low memory algorithm. I wasn't cheating with this random each. Okay, and good. Each vertex, let's say u in 1 to n, will, wants to keep track of its, I'll describe what this means, signed neighborhood as an n choose 2 dimensional vector. Okay. So, let me show what I mean by this thing. So let's say that we have the vertex 3, and it has edges to 1, and it has an edge to 1, and it has an edge to 5. Okay. So 5 choose 2, I believe, is 10. So the possible edges here are what? There's 1, 2, there's 1, 3, there's 1, 4, there's 1, 5, there's 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5, right? These are the n choose 2, the 5 choose 2 edges that could possibly exist in a 5 vertex graph. And let's say, there's also 2 and 4 out here. And let me draw for you what x3 would look like. So any edge that doesn't touch 3 I put a 0 there. So this doesn't touch 3, this doesn't touch 3, this doesn't touch 3. All these don't touch 3. And now 3, 4 is also not an edge, so I put a 0 there as well. Okay, so I think we have 1, 2, 3, 4, yeah, we have 7 left. Those are real edges. 1 is less than 3, so I'll put 2, 3 is not a real edge either. There's no 2, 3. 1 is less than 3, so I'll put a 1 here. But 3 is less than 5, so I'll put a -1 here. Okay. So this is what I'm calling, this is a definition by example. This is what I'm calling the sign neighborhood vector. It's basically an indicator vector. It's an n choose 2 dimensional vector that tells you which vectors are adjacent to you, to 3 in this case. And I sign an edge based on whether u is the smaller vertex in the edge, or it's the larger vertex in the edge. If it's the smaller vertex in the edge, I make it a -1. If it's the larger vertex in the edge, I make it a +1. It doesn't really matter that I did it that way as long as I'm consistent. I could have also defined the signs to be the other way as long as I'm consistent across all of the XUs. Okay? So if in memory I stored, this sounds like it's not clear why I'm doing this, because I just, there's already an n-squared algorithm, which is I remember all the edges in the graph. Now it sounds like I traded in my n-squared algorithm for an n-cubed algorithm, because every vector is remembering an n choose 2 dimensional vector, and there are n vertices. So the total number of entries I'm remembering altogether is roughly n cubed. Okay, but what we're actually going to store is not all the XUs, but we'll store in memory pi, what did I call them? Pi 1 up to pi r. Pi 1 XU, pi 2 XU, and pi r XU for all u. Oops. Okay, so each one of these, remember, to store this takes log 1 over delta times log squared n bits. I'm going to set delta to be like some 1 over poly n for some, 1 over n to the 5th or something like that. Okay. And then I already said that r is theta log n. That implies that the total memory is, right, n times, this is the number of vertices, times log cubed n. This is the space per pi j xu times log n. This is r. So this is altogether n log to the 4th of n, right? It's possible to actually improve this to n log cubed n without really changing the algorithm that much. Basically, the way I'll just say how you do it, but what I'll actually show you is this log to the 4th algorithm. The way you get down to log cubed is you slightly redefine the support find subroutine. So the support find subroutine, I said, with probability delta, you're allowed to like mess up and say something that's not actually in the support. And with probability 1 minus delta, you have to output something that's in the support. Okay, and I showed we've seen how to solve that problem and get log 1 over delta log squared n bits. The way that you do better for dynamic spanning forest is you slightly redefine the subroutine as follows. You say, look, actually, I want to have 2 failure modes: silent failures and known failures. A known failure is the support find data structure just outputs fail. It says, you know what, something is definitely wrong. I'm going to output fail. Okay. And then a silent failure is it just behaves in an arbitrary way. It doesn't know that it failed, but it outputs something that's not actually in the support. So that's failure mode 2. And then I assign 2 different failure probabilities. I say, look, I want failure probability delta 1. Failure mode 1, I want to happen with probability at most delta 1, where it outputs fail. It knows it failed. Failure mode 2, which is the silent failures, I want that to happen with probability at most delta 2. And then if you and then you can get a space bound for this variant of the problem that depends on both delta 1 and delta 2 in different ways. And then what you do is you run this AGM sketch where delta 1 is like a constant, like 1/10 or something. And then delta 2 is 1 over poly n. And if you do that, you can show that, in fact, you'll get an n log cubed n algorithm, and that it's enough, it's enough to make the AGM sketch work. But right now, I'll just assume that we only have failure modes of type 2, which is the worst kind of failure. It's a silent failure. You don't know you failed. And I'm basically setting delta to be so small that it's unlikely that any queries you ever execute are ever fail. So the total number of queries we're going to do here is going to be something like, I think at most n times r, where r is the capital R is the number of rounds. I'm making at most nr queries, which is n log n. But delta has failure probability much less than 1 over poly n, let's say 1 over n cubed. So by a union bound, it's very unlikely that any of my queries fail. Anyway, so good. So now let's think about why storing these pi j xu's is enough to be able to solve dynamic spanning forest. So before I do that, first let's just talk about an offline algorithm. This is for spanning tree. Or spanning forest. Doesn't matter. So okay, so let's say this is my graph. I'm going to imagine solving this in rounds. I'm trying to find a spanning forest. I'm going to find the spanning forest in rounds. In each round, each vertex is going to pick one of its incident edges. Okay? And then we're going to just toss that edge into the spanning forest. All the ones that were picked. So for example, let's give these vertices names. So vertex 1 says, I want to pick this edge. Vertex 2, it might pick the same edge, it might not. Let's say this is being done in a distributed fashion. There's no coordination, but he might just happen to pick the same edge. Vertex 3 decides to pick this edge, which 5 obviously has to because that's its only edge. 4 has to pick this because that's its only edge. Maybe 6 picks this, as does 7, and 8 picks that edge. Okay. So then now what I do is I toss all those in. I toss all those in my spanning forest, and then I contract. So that edge got tossed in, that edge got tossed in, that edge got tossed in. These two edges got tossed in. And then I contract into components. So think of this now as this blob as one mega vertex. This blob is also one super vertex. This blob is one super vertex. And now what I do is, again, I look at edges that leave the super vertices. So for example, there is an edge 7-8, right? But 7-8 to me is not an interesting edge because it does not go outside of a super vertex. It stays inside the same super vertex. I only care about edges that leave a super vertex. So for example, this edge goes from one super vertex to another, as does this one. And then I'll do the same thing. So this was round 1. This is round 2. And then in round 2, I'm going to do the same thing as round 1. Every super vertex is going to pick an edge incident upon it if one exists. That super vertex in the bottom right, there is no edge incident upon it, so it can't do anything. But the other two, they'll pick incident edges. So maybe they both pick this one. And then now I'm done, basically, right? Now my blobs are the connected components. Of course, it might happen that I introduce cycles, but for my purposes, I don't really care as long as I have, because I can always remove the cycles at the end, right? I'm just trying to find the connected components and at least the spanning tree in the component. If I find even more edges than a spanning tree, all the merrier. I can just remove that in post-processing. Okay, so right, does this process that I described make sense for finding connected components and spanning trees inside of them in an offline setting? If I don't care about memory and I don't care about runtime, it's just some process. Notice also that the number of rounds is at most going to be log base 2 of n. Right? Why is that? Just because if you look at the set of non-maximal components, okay, from round to round, the number of non-maximal components, meaning that they're not the final connected component, at least halves in every round. When you go from one round to the next, it divides by 2. Right? And in the beginning, the number of non-maximal components is at most n. Every vertex is by itself in its own kind of blob, and every vertex is its own super vertex. So the number of rounds before you have no maximal components, no non-maximal components, is at most log base 2 of n, which is related to why I chose R. R basically is the number of rounds that we're going to run the randomized algorithm for in the streaming model. Okay. So good. So now let me just convince you that we can simulate this this log n round offline algorithm in a randomized way using the sketches that we've stored. To pick an incident edge. Okay, that's easy enough. Pi1x, can people still hear me? I'm getting error messages about my internet connection. I think it's fine, right? Hello? Testing, testing.
Yeah, I can hear you at least.
Okay, great. So, right, so how do we simulate round one? We just look at pi1 xu for every u. That's a support fine data structure, right? What is xu? Remember, it's just this signed neighborhood vector. And we just do a query, and it returns to us an element of the support, namely an edge that's actually incident upon the vertex. Okay? So round one is easy, right? You just query all these pi1 xus. And some of them might fail. Oh, actually, we're going to condition on the event that none of the queries ever fail, right? Remember, we set delta to be less than 1 over poly n. We're only doing n queries right now. It's unlikely that any of them fail. Okay, good. Okay. Now what? How do we simulate round two? We need to merge things into, we need to merge vertices along these edges that were chosen. And this is I think where the magic happens. Basically, let's look at this picture again, right? Here's x3. Let's ask ourselves, what does x5 look like? x5 looks something like this. Okay. It has the edge to 3. 5 is bigger than 3, so that's a +1. It has, and that's its only edge, actually. It doesn't have any other edges. What happens when you add x3 to x5? Right? The edge 3, 5. So let's say that, in round one of the edges that you're trying to merge along is the edge from 3 to 5. Vertex 3 chose 5, or vertex 5 chose 3 as its neighbor in round one. So you need to merge along this edge. So what I suggest you do is you just add the corresponding vectors. You add x3 to x5. What happens to the edge 3, 5? It disappears because they have that edge has an opposite sign for 5 and 3. But notice that x3 plus x5 is not the 0 vector. It still has in its support 1, 3, right? And my claim is just, in general, if you have two super vertices, okay, basically you can represent each super vertex as the sum of the xu's for u in that vertex. And if you add those two vectors together, what you'll get back is a new vector whose support is exactly the set of edges that leave the super vertex. Okay. So the claim is that for a super vertex is just a set of vertices that got merged. So let's call it A, which is some subset of the vertices. Let its vector be xa, which is defined to be the sum over all u and a of xu. Then the support of xa is exactly the set of edges, leaving A, or crossing the cut from A to n minus A. So that's basically what I'll do, right? If in round one, if the edge 3, 5 is chosen to merge, I'll add, I'm not storing x3 and x5, I'm storing pi times those. I'll add pi 2 x3 and pi 2 x5, okay? And I'll add pi 3x, sorry, if I merge the edge 2, 5, I'll add pi 2x, 3, 5, pi 2x3, pi 2x5, pi 3x3, pi 3x5, pi 4x3, pi 4x5. Basically, in all the future rounds, I'll just make sure to add the sketches of those vectors together. And then in round two, I'll query to figure out which edges to merge using pi 2. And then in round 3, I'll use pi 3, etc. So question for you I'm using an R factor larger memory because I have R different sketches for each vertex. Why do I do that? Why don't I just store pi xu? Just always use the same matrix pi. In round one, I'll query all the pi xu's. I'll get some edges to merge. I'll add the corresponding pi xu's together. Now in round two, I'll query those pi xa's, where a's are the super vertices. I'll get some edges, I'll merge them, etc. Right? I've just saved myself a factor R memory. Why don't I do that? What's the problem there? Anyone see any issues? So it's slightly subtle. What does it mean to have a randomized algorithm that works, or like a randomized data structure? Let's say a data structure, a randomized data structure that works. Let's say randomized. So a randomized algorithm, a Monte Carlo randomized algorithm, says that for all inputs x, the probability over the random coins tossed by the algorithm A of this is for all inputs x. The probability that A is correct on input x is at least 1 minus delta, right? That's usually what we mean when we say that we have a randomized algorithm that works with high probability. When you say this, x is fixed in advance. You're not allowed to have the query to have the input x depend on the random coins. Let's say the random coins tossed by A, that's a random string R. You're not allowed to first look at R and then based on R choose x. Okay, and that's exactly what you would be doing if you only used one matrix pi. Because the point is, you queried all the pi xu's in the first round. That told you which edges to merge. Okay. And then you merge. So basically, the edges that you're choosing to merge depend on the randomness that defines pi. The randomness that defines pi is just the hash function h, if you unravel what all this means. So based on that hash function h in the definition of your support find data structure, you chose what to merge, and then when you do a query in your second round, the fact that you're doing that query is correlated with the fact that you had that as your H, right? So what you're choosing to query in later rounds is correlated with the randomness of the algorithm itself. And that's not allowed in Monte Carlo randomized algorithms. You're not allowed to have inputs that depend on the randomness. Kind of all correctness guarantees are off. And that's exactly why I use a different randomness for my sketching from round to round. Because pi 2 is a random sketching matrix chosen independently of pi 1. And pi 3 is chosen independently of pi 1 and pi 2. They're all independent of each other. So the queries I'm making in my jth round of this algorithm are not correlated with the randomness of pi j. So I do get the correctness guarantees promised to me. And in fact, it turns out that that's actually not just an artifact of the analysis, that's needed. Because I told you that there's an n log cubed. I told you that there's a way to modify support find to be this kind of 2 failure mode support find to get an n log cubed n algorithm. Other than modifying the support find subroutine, everything else is the same. You're still using capital R rounds. Capital R is log n. In fact, capital R in this case could actually be, exactly kind of log base 2 of n. In the case where there are 2 failure modes, you actually have to make it some larger constant times log n because, let me not get into that right now. But anyway, the point is just, if I could get away with only having 1 pi and not having r pi's, I would actually get an n log squared n algorithm. And that violates a lower bound. Remember, I told you that we have a lower bound saying you actually need n log cubed n bits of memory to solve this problem. There's a provable lower bound. So it's interesting that, I mean, you might look at this argument and say, oh, that's just some technicality that Jelani needs to perform to make the analysis go through. But probably in practice, I can get away with just using a single pi in all the rounds. No. Okay. No, we know for a fact that you do need to use different pi's in every round, because otherwise you would have too good of an algorithm that would violate the lower bound. And I'm going to give you some practice with this kind of reasoning in the first homework, which will be out soon. Okay. Okay, so that's all I have for you today. I'm basically out of time. Any final questions?